Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into the flight booking system, the engine that powers every airline ticket search, fare comparison, seat selection, reservation, and checkout you have ever used. We'll cover how platforms handle millions of searches, real-time inventory, global distribution systems, pricing rules, and last seat reservations. Whether you're preparing for a senior engineering interview or building travel infrastructure at scale, this one is for you. Let's get into it. Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into the flight booking system, the engine that powers every airline ticket search, fare comparison, seat selection, reservation, and checkout you have ever used. Whether you are booking on an airline website, an online travel agency like Expedia, or a meta search engine like Google Flights, the same hard problems show up. Inventory must be accurate, prices must update in real time, seats must not be double sold, and payments must complete before a reservation is guaranteed. If you have ever wondered how these systems handle millions of searches per day, complex fare rules, global distribution systems, and last seat inventory, this video is for you. We'll walk through the functional requirements, non-functional requirements, system architecture, end-to-end user journey, core models, low-level design, and the trade-offs that come up in a senior system design interview. Whether you are preparing for a FAANG interview or building travel infrastructure, let's get into it. Here is the core problem. A traveler searches for a flight from New York to London. In one session, they may see results from a dozen airlines, multiple fare classes, and various connection options. The prices look attractive, but the moment they try to book, the fare is gone, or the seat they selected is no longer available, or the price has jumped. On the other side, airlines and travel agencies operate a global, distributed inventory. Seats are sold through direct websites, online travel agencies, global distribution systems, and call centers. A flight has only a few hundred seats, but millions of users search simultaneously. Stale cache, race conditions, and partial failures can cause overbooking, double bookings, or phantom inventory. The business needs a reliable, scalable, and consistent flight booking system that shows real-time availability, locks inventory during checkout, processes payments, issues tickets, and handles cancellations and refunds correctly. Let's walk through the functional requirements. First, the system must support flight search. Users enter origin, destination, dates, and passengers, and receive ranked results with prices, durations, layovers, and airlines. Second, it must provide fare and availability display, including cabin class, baggage allowance, refund rules, and real-time seat count. Third, it must implement a booking flow. Select flights, enter passenger details, choose seats and add-ons, hold inventory temporarily, and proceed to payment. Fourth, it must handle reservations through a passenger name record, or PNR, that stores itinerary, passenger information, contact details, and ticket status. Fifth, it must integrate with payment gateways, issue tickets upon successful payment, and support modifications, cancellations, and refunds. Sixth, the system should connect to airlines and global distribution systems for inventory and pricing, and send notifications via email and SMS. These capabilities are the backbone of any serious flight booking platform. Now the non-functional requirements. The search and availability layer must be extremely low latency. A user expects results within a few hundred milliseconds. The inventory layer must be strongly consistent. Selling the same last seat twice is unacceptable. The system must be highly available, because bookings happen 24 hours a day across every time zone. It must be scalable to handle millions of searches per day and traffic spikes during holiday sales. The system must be accurate on pricing, taxes, currency conversion, and bag rules. It must be secure since it handles personal information, passports, payment details, and PNR records. It must also be resilient to upstream failures, because an airline global distribution system may be slow or unavailable. And finally, the audit and compliance trail must be complete, because refunds and disputes depend on it. Here is the high-level system architecture. On the left, Users and partner systems send search and booking requests through a content delivery network and an API gateway. The search service talks to a flight search index and a cached inventory snapshot to return fast results. For live availability and pricing, it calls a global distribution system adapter or direct airline connections. The booking service orchestrates the reservation flow. It locks inventory, creates a PNR, collects passenger details, and initiates payment. A payment service integrates with payment gateways and confirms successful transactions. The ticketing service issues electronic tickets and updates the PNR status. An inventory management service keeps track of seat counts, holds, and releases. A notification service sends emails, SMS, and push alerts. A data analytics backend stores booking trends, search logs, and revenue reports. The key metrics to memorize: cold search latency, the P95 time from query to results page. Availability accuracy, the percentage of displayed fares that are actually bookable. Booking conversion rate, the fraction of searches that turn into confirmed tickets. Inventory consistency, the number of overbooking or double booking incidents. Payment success rate, the percentage of payments that complete without retry. PNR creation and confirmation time, the time from passenger details to a confirmed reservation. Revenue per search and revenue per booking, used to optimize caching and ranking. And cancellation or refund processing time, because customer trust depends on it. These metrics are what the business actually cares about. Let's trace the end-to-end user journey. A traveler opens the app and searches for New York to London on a specific date. The search service returns a list of flights with prices, durations, and baggage rules in under half a second. She picks a non-stop flight, selects a window seat, and adds one checked bag. The system places a temporary inventory hold for 5 minutes, creates a preliminary PNR, and redirects her to payment. She enters her card details, the payment gateway authorizes the charge, and the ticketing service confirms the booking. The system sends an email with the PNR, ticket number, and e-ticket. If she cancels within 24 hours, the refund service reverses the payment and releases the seat back to inventory. Every step depends on low latency, strong consistency, and reliable upstream integration. The core models and algorithms. The flight schedule model defines routes, aircraft, departure times, and capacity. The inventory model tracks seats remaining in each fare bucket and booking class. The pricing model applies fare rules, taxes, surcharges, and currency conversion. The seat map model represents the physical layout, availability, and reserved or blocked seats. The PNR model is the central reservation record containing passenger names, itinerary segments, contact details, and ticket status. The booking state machine moves from quote to hold to payment pending to confirm to ticketed to canceled. The hold mechanism uses a time-bound inventory lock to prevent double selling. The cache invalidation strategy balances freshness with latency. The key trade-off is consistency versus performance. Stronger guarantees usually mean slower searches and higher dependency on live systems. Now the low-level design deep dive. The search index is built from schedule and inventory snapshots and is optimized for fast filtering by origin, destination, date, and cabin class. Inventory reservations are tracked in a transactional store with row-level locking or atomic decrement operations. The PNR service stores records in a relational database with strong consistency, indexed by passenger name, booking reference, and flight date. The pricing engine evaluates fare rules using a rules engine that combines flight, date, passenger type, and channel. The payment service uses idempotency keys to avoid double charging and supports both synchronous and asynchronous confirmations. The booking orchestrator uses a saga pattern. If any step fails, previous steps are compensated, such as releasing an inventory hold or refunding a payment. For high-traffic routes, inventory is partitioned by flight or date, and caching layers use short TTLs with proactive invalidation. Key takeaways for your interview. First, a flight booking system is a distributed inventory and reservation problem, so emphasize concurrency control, holds, and eventual consistency. Second, Always distinguish between the read-heavy search layer and the write-heavy booking layer, because they optimize for very different things. Third, the PNR and ticketing state machine are central to correctness, so be ready to design the transitions and failure compensation. Fourth, the hardest design challenge is balancing low-latency search with accurate inventory, which usually requires tiered caching, live lookups, and careful hold management. Fifth, reliability and payments are non-negotiable. Mention idempotency, retries, timeout handling, and the saga pattern. If you can walk through this system with these 5 points, you will signal strong senior-level design thinking. That's it for the flight booking system. If this helped, like and subscribe, and I'll see you in the next one at Cloud Wizard. And that's a wrap on the flight booking system. We covered the full picture, from search and live availability, through inventory holds, PNRs, ticketing, payments, and the low-level saga design that keeps it all consistent. If this video helped you, please hit that subscribe button and the bell icon so you never miss a new system design video. Drop your questions in the comments below. I read every single one. See you in the next one at Cloud Wizard.